Greetings to all of the students in the 10 Years Hence course. My name is Kevin Bowyer. I've been looking forward to making this presentation live and in person with you, but so if you have questions after you watch this presentation, feel free to shoot me a note and ask. The title of the talk is Face Recognition and Privacy, Past, Present, and Future. The past, present, future will kind of correspond to three pieces of the talk. And I'm revisiting face recognition and privacy concerns from a past interest of mine, and I'll explain that to you in a moment. I hold the position of the Shub-Mel-Prine Family Professor of Computer Science and Engineering. And June Prine, if you happen to be watching this talk at some point, thank you very much for your support over the years. In the interest of sort of being open about possible biases, I am biases that might influence things I say here. I am have a technical advisor relationship to three different startups in the biometric space. Asignio, which is actually part of the Notre Dame family in the sense that there's a Notre Dame alum who was one of the founders. Asignio has a very interesting dynamic handwriting approach to identity verification, and the handwriting being done on the touch-sensitive screen of mobile devices. FaceTech does identity verification with three-dimensional face recognition, and Yambu does identity verification with fingerprints. So three very different biometric identification startups, all doing very interesting things. I'm kind of excited about all of the prospects for all three of them. And I don't think that my relationship with them has any influence on what I'm going to say in this presentation. Another bias is that I'm a career academic. I've worked in research at University of Notre Dame and University of South Florida before that for a number of years. I am a fellow of three different professional societies, the most recent being the American Association for the Advancement of Science. Those are just academic credentials recognizing your research accomplishments. More to the point for this talk, I currently serve as the editor-in-chief for the IEEE Transactions on Biometrics, Behavior, and Identity Science. This gives me a chance to see state-of-the-art developments in biometrics broadly across the board, biometrics and identity science. And so if this brings a bias, it brings something of an academic research bias to my thoughts about security and privacy and face recognition. About 15 years ago, I sort of in the context of the aftermath of 9/11 and the use of face recognition in counterterrorism applications, I wrote a paper called Face Recognition Technology, Security versus Privacy that received an award of excellence and appeared in the IEEE Technology and Society magazine. A lot has changed since then. I didn't realize how much has changed since then until I went to put together this talk. And the field has changed, the issues have changed, the concerns have changed. Maybe that won't be as obvious to you, but it was obvious to me bringing this forward, and I want to try to give you a feeling for some of that. As I said, the talk will be structured in three parts. A little bit about the past, because you need to understand the velocity with which the field is changing in order to appreciate how fast things that we think are in the future may come upon us. The present you need to understand, because the future will to some degree come out of what we think of as the present. Now, the present isn't this particular month or this particular year, it's sort of last year, this year, and next year. Past is things further in the past, and future elements are things that are coming out of the present going forward. The biggest message to take away from the past and face recognition is a feel for the speed with which things are changing, and in particular with which the standards for accuracy of face recognition are changing. This slide is meant to make the point that face recognition as a field, face recognition by computer as a field of research, is about 50 years old. This is a figure from Takeo Kanade's PhD dissertation. Takeo Kanade went on to become one of the best known senior researchers in computer vision and robotics. He directed the Robotics Institute at Carnegie Mellon for a number of years. This is his PhD dissertation, sort of where his research career started. You can see that they were talking about doing what was called a binary picture of the human face, that is the edges that are apparent in the normal image of the human face, and a representation extracted from those edges as being the means to recognize someone in the image. That's not at all how it's done now, but this, if you're a little bit technical, might give you a feel for how primitive things were at that point in time. Not a whole lot of advancement in face recognition for a while. I'm going to jump forward 25 years really quickly to something called eigenfaces. Eigenfaces was a part of Matthew Turk's PhD dissertation, and it captured the imagination of the computer vision field, the face recognition field, in a really big way, and became the dominant paradigm for looking at face recognition and things related to face recognition for a decade or two afterward. The citation numbers here that you see for these papers coming out of Matt's PhD dissertation are just phenomenal. Again, very, very influential work. The essence of the idea, and we'll spend just like a sentence on it. If you don't get it, that's okay. It's not essential, but it was that you would take each image of a face represented as a row in a large matrix, solve the eigenvalue decomposition for this large matrix, and the eigenvalues would represent dimensions of variation of the face images that you had given to the algorithm to train on or to learn on. So it was a way of learning a representation of faces from a set of face images, example images that you give it, and using that to do recognition. As I said, this was the dominant way of thinking about face recognition for a long, long time. More recently, the idea of using deep convolutional neural networks has taken over as the dominant way of thinking about face recognition and many other topics in computer vision and in artificial intelligence and in engineering broadly. The particular example of a deep convolutional neural network that my lab uses at the moment in most of its work is called ArcFace. And ArcFace comes from the Imperial College Research Group in London. I'm going to explain it as if it's made up of three major concepts. One is the use of ResNet, which was a prior structure for a deep convolutional neural network called residual network, and it uses this basic building block for how to structure the network. There's actually several common variations of ResNet. There's a particular one that ArcFace uses. Then if you're using a deep convolutional neural network, you have to have a set of data to train on. The data that ArcFace is trained on is the Microsoft, that's the MS celebrity data set, images scraped from the web of celebrities, and originally about 1 million of those. This is version 2, and the creation of version 2 is particular to the Imperial College Group wanting to train ResNet and get the highest accuracy they could. They noted that there was a certain amount of noise in the MS Celeb 1 million original data set, in the sense that if there were 100 images that were nominally supposed to be of Kevin Bowyer, it might be that 80 of them were of Kevin Bowyer and the other 20 were of other people who had appeared in pictures with Kevin Bowyer that were posted on the internet or something like that. And that by going through and cleaning the data set, even though you ended up with fewer images as a result, you could get a better training of the neural network. And so that was an insight of the Imperial College Group that went into creating ArcFace. And then the third concept for understanding ArcFace is that they perceived the idea of representing people as regions or images, a collection of images of a person as a region on a very high dimensional hypersphere. And you want to sort of maximize the distance between the regions that represent different people. In retrospect, these collection of concepts may sound simple, but this was a major advance in, even within deep neural networks for face recognition. ArcFace is a major advance, and it's probably in the top 5 algorithms currently. And you can get the source code, so to speak, for it for free because it's an academic invention. This particular slide is kind of summarizing the past in face recognition. And the point of this slide is simply to say that the absolute accuracy of face recognition has improved in dramatic terms. You can talk about error rates in half every 18 months or 2 years over a period of 20 years or something like that. Let me explain this diagram. This plot comes from Jonathan Phillips at the National Institute of Standards, a great friend and colleague that I've worked with in the past. And this represents his way of conceptualizing the accuracy of face recognition over time as measured in various government programs by the US government, which tried to benchmark the use of face recognition. So back in 1993, this would have been not long after eigenfaces sort of captured the imagination. The government benchmarked the accuracy of face recognition, and they set the false accept rate at 1 in 1,000. A way of thinking about that is that if you were matching everyone who walked by your house, 1,000 people, you would have to bring by 1,000 to get one who was likely to match you. So if you set the threshold at that level of security, only 1 in 1,000 random people would have a chance to match as you, then the false reject rate at that false accept rate, or that security rate, was 79%. That means if you wanted to be recognized as you would have a 79% chance of not being recognized correctly and only a 21% chance of being recognized correctly. That trade-off, that level of security and that level of non-usability doesn't sound very interesting. But note, only a few years later, the false reject rate was down to 50%. And a few years after that, the false reject rate was down to only 20%. The color coding here is indicating that the field had sort of shifted to a larger data set of face images in order to be able to benchmark things. And a few years later, still, we're down to 0.26 chance of you not being able to be recognized as you, when only 1 in 1,000 among a population of strangers could manage to get recognized as you. And then it went down even lower. And then this diagram is, this bar on the diagram is indicating that they switched in the evaluations to a different problem task, a harder problem task, and a larger data set. So the color coding of the bar and the fact that it's to the right of the line there. We're now looking at rank 1 retrieval rate. So if I take a picture of someone and I match against a very large database of all sorts of different people, and I bring back the picture that the algorithm says is the closest matching picture, is it the right identity? Is it the person in the probe image that I gave to the search? And the rank 1, the probability of making an error on the rank 1 retrieval is again headed down to where it's almost negligible. So again, the point of this is that in the last 20 years, the accuracy of face recognition has gone from unusable to where the error rate is actually hard to measure because you don't have a data set large enough to measure it reliably. Okay, from the past, advances in recognition accuracy, but recognition wasn't the only thing that was going on in face recognition. There were analytics done on face images to find out things other than identity. One of the really popular things that's seen a large amount of research and that is a part of the field called affective computing is to be able to recognize the facial expression or the emotion behind the facial expression of a person in an image. And Hattie Skoons is one of the leaders in this area. She is also in the UK. And these basic emotions are part of a theory by Paul Ekman in psychology, that there are primitive emotions that correspond to primitive facial expressions that are general across gender and race and geography. And so a lot of work has gone into being able to process a face image to say whether it's representing happy, sad, surprised, disgusted, things like that. A lot of commercial tools exist that will process an image for you and tell you, in theory, what the emotion the person is expressing in that image. The field of getting other properties of a person from their face image is sometimes called soft biometrics. So biometrics can be done from things other than face image. In a survey paper by Antitsa and Arun, other great people, and Petros in our field, demographic attributes such as the age of the person can be estimated, the gender of the person, the ethnicity, eye, hair, and skin color, some body geometry and facial geometry settings. There's, and medical attributes we're going to return to because that's going to be a theme. Being able to get some insight into the health of the person from their face image and knowing something about the things that they're wearing, which might be used in a re-identification task if someone goes out of the field of one camera and into the field of another camera. So face analytics has broader than any one of these things. It's sort of all of these things, and the health attributes is something that we're going to look at in more detail. One particular health attribute that may seem almost like magic is that you can find a person's heart rate from a normal video stream in which you can see their face. This was popularized by Roz Picard at MIT. It was not part of her PhD dissertation. It was well after that. I know that we mentioned PhD dissertations earlier for Matt Turk and for Takeo Kanade. But this problem has been solved several different ways, to the point where there are now review articles comparing the pros and cons of different approaches to heart rate measurement from frontal videos of the face. So this is a known technology that can sort of be used almost off the shelf these days, and though there is a bit of re-implementation perhaps and customization of the algorithm to work in a particular setting. Okay, so the two themes from the past: incredible progress in accuracy of face recognition and broad exploration of other things, other pieces of information that you might be able to get from a face image. If we begin to look at the present, what are the dominant themes that are going on currently in face recognition? One of those, and one that I'm choosing to emphasize because our lab is involved in this, is demographic accuracy differences. Is the accuracy of face recognition different for different identifiable demographic groups? And if it is, why, and what is the implication of that, or what does that mean? So the National Institute of Standards in the United States released a face recognition vendor test. They can collect face recognition algorithms from different vendors and benchmark them on data that's available to the National Institute of Standards. And they released this report, and the media coverage was relentlessly negative. This is MIT Technology Review saying that a US government study confirms that most face recognition systems are racist. I don't think that's the way it was worded in the National Institute of Standards report. New York Times, the racist history behind facial recognition. Another news report, techno-racism. And my favorite, not favorite because I like it, but favorite because it's the most extreme. The headline, NIST confirms that facial recognition is a racist, sexist dumpster fire. I am certain that that's not the way it was worded in the National Institute of Standards report. It is a property of the world we live in that all online news sources need to draw you to them and have you click on them. That's how they make their money. And to some degree, that produces a motivation to write a headline which is motivated by the probability, the perceived probability of that headline getting you to click on the article rather than justified by the content of the article. And obviously, I'm suggesting that some of these headlines are more clickbait than reality. The research that I'm about to talk about is a joint project between Florida Institute of Technology. Those are the three people you see on the top row there, and Notre Dame. Those are the two people you see on the bottom row. The bottom right is myself. The other person in the bottom row is Vitor Albiero, who's a PhD student here. Krishnapriya Kushal and my colleague Michael King, Dr. Michael King, are in the top row there. Now, we have done a fair amount of work on comparing accuracy of face recognition for a data set of Caucasian images and a data set of African American images. They're separated out here, male and female results, male on this side, female on this side. The threshold along the bottom, absolute similarity, the images have to be identical, would be here. Substantial dissimilarity would be over here. And the rate of two different errors is on this side. So false matches, the chance that two images will incorrectly be said to come from the same person, as you make the threshold for two images being accepted as a match higher and higher, the probability of a false match declines. At any given threshold, the Caucasian males have a lower false match rate, a lower false match error rate than the Caucasian males have a lower threshold than the African American males. African American males have a higher error rate of false matches. Coming this direction, if we insist on perfect matches, then everything is a false non-match. Everything other than a copy of an image is a false non-match. If we relax the need for perfect matches, then I can have more variability in my facial expression and appearance, and I will still match myself. And so at any given threshold, if I draw a line up, I find out that African American males have a lower false non-match rate. That is, they're denied entry by saying you don't match yourself, you don't match who you claim to be. They have a lower error rate of that type of error than do Caucasian males. So the fact of the situation is that there's two different error rates, and that each demographic group is advantaged by one of the two error rates and disadvantaged on the other of the two error rates. The same situation is true if we look at female African American and female Caucasian. African Americans have a higher false match rate. Caucasians have a higher false non-match rate. The way that I prefer to look at these is in terms of the imposter and the genuine distribution. This is an imposter distribution. This is the matching scores of all pairs of images where the two images actually belong to different people. This is an example of an authentic distribution or a genuine distribution. This is the matching scores between all pairs of images in the data set where the two images belong to the same person. And if we look at this and we divide it out by African American and Caucasian, we see that Caucasians have an imposter distribution centered over lower scores than African American. So this gap here is increased false match rate for African Americans. But if we come over here, we see that this area under the two curves is the increased false non-match rate for Caucasians in comparison to African Americans. There is a concept called the separability of these two distributions. A statistic for measuring that separability is the D prime statistic. If we look at the D prime, that is how well separated are the imposter matches from the genuine matches for Caucasians, and the imposter matches from the genuine matches for African Americans, we see that African Americans actually have a very slightly larger D prime, indicating that the two distributions are more separable. The technical implication of this is that state-of-the-art face recognition has slightly more power to recognize correctly African Americans than Caucasians. Not at all what you might expect from the headlines you might have seen in the media, but this work is done with a deep neural network that you can obtain if you wanted to, and a data set that you could obtain if you wanted to. So anyone can reproduce this result and sort of check that we did it correctly if they were motivated to. This is showing the difference between male and female. We've sort of pulled out some of those curves from the separate plots on the previous slide and put them on this slide. The situation for women is a little different than the situation between male and female is a little different than the situation between African American and Caucasian. In this case, the red is for female. This is the red imposter distribution, and it's shifted higher. That's indicating more false match errors for women. But when we come over here, the red for the genuine distribution is shifted to lower. So this area coming down here is indicating more false non-match errors for women. So women, compared to men, are disadvantaged on both types of errors. They're losing on both error rates. Why do African Americans have a higher false match rate than Caucasians, and Caucasians a higher false non-match rate than African Americans? Why do women have a higher false match rate and a higher false non-match rate than men? Great research questions. No one yet knows the answer to these. We think that in the next couple of months, we will have the answer on the gender issue, and that we will be able to use that as leverage for answer on the race issue, but the work is not finished and certainly not published yet. And there are other groups that could well scoop us to the results. So to give you some more further insight into this, it does appear that women on average wear cosmetics more than men. That is, if you look through the face image data sets and you separate out the obvious instances of cosmetics, you'll see it in women. You probably won't see very many in men. Women, it is true that women are shorter, and that if the camera is mounted at a fixed height, that would give it a downward looking view towards more women's faces than men's faces. One that was a little bit surprising to me, someone said women are very expressive when their picture is being taken and men are more stoic. And my first reaction was, that sounds crazy. But when you actually go and look at that, that's true. In some of the data sets that we've analyzed, there is more variability in the facial expression for the women than for the men. And another factor, women are certainly less represented in the data sets that are used to train deep neural networks. But from our research, none of those factors account for the accuracy differences that you saw on the previous slides. How do we figure that out? Well, this row and this row represent two different commercial tools for predicting the facial expression of the person in the image. And you notice that neutral expression is the most common expression predicted in all cases, but that men are recognized by the algorithm as making a neutral expression substantially more than women are, and women are recognized as making more different expressions by either tool. You also notice that comparing these two tools, results were coming from the same set of images. So either this tool is sort of hallucinating more variability in an expression, or this one has a higher threshold for recognizing a different expression. I think that the answer is more that this one is catching the true variability expression, and this one is suppressing it a little bit. But set that aside. If we take the subset of images on which these two commercial tools agree that the person is making a neutral expression that does not have any of the off neutral expressions in the image, and we recompute the imposter and genuine curves, we ask then, does the imposter and genuine with only the neutral expression face images cause the problem to go away? And if you compare these, you can see that the problem is there in both the top and the bottom, indicating that variability in facial expression was not the cause of the differential performance between males and females that we presented. We've done similar sorts of studies for the other factors just mentioned, and we recently think we have a line on what is the cause of the difference, but I won't present that in this talk, maybe a future talk. Another big theme currently important in sort of all commerce having to do with face recognition, but something that gets attention in research as well, are social and legal sorts of issues. I'll give you an example of that. In the burst of publicity over the last year or two about face recognition being biased and sexist and racist, some municipalities decided to ban the use of face recognition. So in 2019, San Francisco became the first municipality to say, we're not going to allow the use of face recognition by city government. Now, they had to change that fairly quickly afterwards because they had given iPhones to city employees, and the way the law was written, the city employees couldn't have iPhones because iPhones had face recognition technology as a part of them. So the law has since been changed to say that it's okay if you are using an object piece of technology which has face recognition, if the face recognition is turned off, or if you absolutely have to do it and there's no other way, no viable alternative, you can use face recognition. This incident illustrates sort of the attempt to make a one-size-fits-all solution to a perceived problem, and then the need to incrementally kind of back off from that one-size-fits-all in order to get something that's practical at all for the city government there. Another different ban is statewide in California, that the body cameras worn by law enforcement cannot be set up so that they feed directly and continuously into a face recognition algorithm, which is matching the pictures taken by the body camera against some set of suspects and providing results real time to the law enforcement person. I actually think this one is at the moment technically well-founded, even though the error rates are phenomenally low on a per image basis and on the rank 1 identity search, as we presented a number of slides back. If the video feed is feeding video all day long for a law enforcement officer, you're sort of, if it's a 1 in a million error and you feed 10 million images to it during the day, you're expecting 10 errors. So this particular use of marrying a video stream to face recognition from a video stream from body camera to face recognition was sort of guaranteed to produce too many false matches, I think, in the current setting, and something is needed to mediate that for this to be practical. A use that may seem counterintuitive at first, and some of you are probably wondering, why in the world does he have a Taylor Swift slide in here? Well, it came out that Taylor Swift concerts were using face recognition without telling the attendees. And the way this worked is that there were kiosks at the concert venue where there were music videos playing, and the thought was that people would come up and cluster around to see the cool video of Taylor Swift rehearsing or doing her latest song or whatever it is that she was doing, and that while people were there clustered around the kiosk, a camera was taking face images of everybody there, segmenting out the face, providing it to a face recognition algorithm, and matching it against a list of known stalkers that she thought presented a security risk to her. So this is personal security for Taylor Swift from stalkers, known stalkers, at her concert venues. So her security people would get an alert if someone in the audience looking at the kiosk matched someone who had been a stalker of her in the past. A lot of concerns about the privacy here because people weren't told about it, and who owns the images. And my understanding is that Taylor Swift told all the critics to just shake it off and go on. A third trend currently is expanded biological and medical inference. Remember, we touched on that earlier, this is something that captures the imagination of a large segment of the research community, and it's getting a lot of work, and it's going to be there in the future part of the presentation as well. There are going to be things that happen there that are going to be fundamental and important. A couple of things that are happening right now that are sort of known technology. I mentioned earlier that we can predict the age of a person from their image. If you also get biographical information on the person, you have the real age and the apparent age, or the chronological age, and the apparent age. And the difference between how old a person is and how old a person looks can have some commercial applications. A colleague of mine, Carl Rixenick at the University of North Carolina in Wilmington, and who's visited Notre Dame campus several times and given talks, is chief scientist for a company called Laptus. And his company has recently been certified as a life expectancy provider, that is, giving information about life expectancy to insurance companies who might underwrite a life insurance policy in the state of Florida. His company will take your face image, get a body mass index calculation, do your estimated age from you, get your chronological age, figure out your gender, can also figure out your race, can get an indication of whether or not you're a long-term smoker. It can also get an indication of whether or not you're a long-term heavy drinker. And from that constellation of information that it's able to get, it's able to provide enough information to insurance companies that they could issue a life insurance policy without the person receiving the policy needing to go to a doctor and getting a blood test, which would be the traditional way of getting life insurance. So it makes life insurance more accessible, perhaps, in that people don't have to go to a doctor and get a blood test, and don't have to do as much work or pay as much to get life insurance. And so it may open up life insurance underwriting to a larger population. It's also maybe a little bit concerning that all this information is readily apparent from your face image, but it is to some level of accuracy. Another application, which I believe is now actually rolled out and exists in some automobiles, is to watch the face image from cameras mounted in the car to determine where your eye is looking, how drowsy you are, and whether or not you're being attentive to the task of driving your automobile. And here is a diagram where you can see that there's a couple of cameras mounted to be able to catch the face in different angles. And I believe some cars now will, in fact, say, you do not appear to be attentive. Why don't you pull over and get some rest, or switch who's driving the car? So this is an example of a very safety-oriented application of facial analytics. And you have to go back to the example of San Francisco banning the use of face recognition technology, and ask, well, would they buy one of these new automobiles that would tell them when the driver, the city employee driver of the car was falling asleep at the wheel? Would they make them turn that off, or would that be another exception written into the law for it's okay to use face recognition technology in this way, just not in some other ways? Final example in this category, there's a company that very recently rushed out, and note the date there, technology that would allow to detect the fever of somebody in an airport without someone having to come up to them and actually take their temperature. I think this is actually using infrared camera, or infrared and normal color camera, to get the temperature. And I think it's probably not reading out the absolute temperature, but just detecting whether or not the temperature is elevated. Nevertheless, the idea that you could do real-time fever detection at a border crossing or in an airport, the value of that kind of technology is brought home by the fact that we are in the social distancing semester here and worried about travel. Okay. Possible future. Some of the things that I'm going to say here. Expanded health analytics. This is an area that captures the imagination of a lot of researchers. There's a lot of people working on it. Advances are happening quickly. There are survey papers out there that sort of have looked at all of the medical conditions, psychological and biological, that might have clues in a facial appearance, or facial appearance measured over time, or facial appearance measured continuously from a video. And they're sort of categorizing those, and initial research has been done. You can tell all of the papers here in these numbers to look at a lot of different things. And I think the number of people working on any one of these topics is growing continuously, and the breadth of topics that's being approached in this work is also expanding continuously. Some of it with standard imaging, some of it with thermal or infrared imaging, some of it with stereo. So different types of technologies, different algorithmic technologies. If you're really interested in this, the senior author here is quite good, and I suggest maybe taking a look at that survey. Mass surveillance and tracking. This was a return to the privacy sorts of concerns in the paper that I wrote 15 years ago. The topic that's getting a lot of play in the media is how China is employing face recognition currently. I don't think they had to, that this topic is peculiar to China, or that the media had to pick on China, but it's what's been in the news lately. Certainly lots of excellent research being done in face recognition in China, lots of companies coming out of China with great technology. This particular article talks about uses of face recognition in different places to find people who have been protesters, anarchist protesters in Chile, perhaps, political protesters in Uganda, or in China. Even the desire to track an entire group, an entire ethnic group of people throughout the entire country of China. So the Uyghurs, pronounced Uyghur, spelled U-Y-G-H-U-R or U-I-G-H-U-R, is a Muslim minority located in the west of China, in a particular province. And for their own reasons, the central government of China has decided that the technology, facial recognition and analytics technology, can be used to recognize Uyghur individuals, or recognize someone who's not necessarily known in a government database yet, who might be a Uyghur, wherever they might travel in the country of China. This activates some of the big brother fears that are always present in the use of technology, and the fact that Uyghurs are believed to be put into re-education camps, which are worse than a re-education, or re-education in the perhaps the old Soviet sense of a re-education camp, makes this very disturbing. There's a number of good videos that I suggest you watch. I'm not going to play them as part of this talk, but the idea that there's a social credit score that determines whether or not you might be eligible to use the train or board a plane. How surveillance works as you move around the country. I would suggest especially if you're not interested in this topic, I think you should watch all three of these videos, because you should be interested in this topic. There shouldn't be a person in the audience who is not interested and concerned about this, and concerned about the future possibility that if the government of China demonstrates success in using the technology for these ends, that it will represent a model for other governments to attempt to do the same thing. Thorny legal issues. I mentioned some of the concerns about how face recognition was being used at a Taylor Swift concert, but it's actually much bigger than that, and multifaceted. Some of the high-tech companies that have social media type applications have realized that there was a company called Clearview AI that was going onto their sites and downloading massive amounts of facial images, presumably to be used in training neural networks or in setting up databases, because as you get the images from Facebook, you might be able to get not just the images, but an identity for those images, and then selling services to our government, but for all we know, potentially to other governments as well. So Facebook, YouTube, other large companies have told Clearview that this violates their policies. Very difficult, I think, to enforce. And if it violates the policies, but it was noticeable only because they were doing it sort of all at once, and it was a recognizable use, some other company could come along that wanted to distribute the use over time and could sort of be under the radar and not be detected, or a group of people could join and combine the data that they were allowed to download within the usage term, the terms of use of the social media application. So this is something this is a problem that's not going to go away and not going to be simple to police, is who can make what uses of the information about a person that they have voluntarily put on a social media site. This particular example, the Illinois Biometric Information Privacy Act, every company that makes any use of biometrics everywhere in the United States needs to know about this. Hopefully they already do. And every startup that comes into existence that thinks it's going to do biometrics needs to know about this, and needs to know that there's a sort of a movement sweeping the country for different state legislatures to enact similar laws. Basically, the law says if you're doing any sort of biometric, you need to have written consent from each subject who does it. You need to have a policy for retention and deletion of the data, and it puts into place a statutory damages for every incident of violation of the law. So damages under the Biometric Information Privacy Act range from $1,000 to $5,000 for each intentional or reckless violation. This sort of law is kind of custom made to generate lawsuits. And so there are enormous lawsuits against companies like Facebook, but also against companies like Lowe's and Home Depot, who might use facial recognition to track people in their stores. And if they have people that have been ejected from their stores for shoplifting in the past, to recognize when those people come in. If they didn't recognize when this law was passed and immediately put in place some procedures to be compliant with this law, then they have now accumulated damages of $1,000 to $5,000 per instance of violation. The math here works out just phenomenally. It could put all sorts of companies out of business. I had been approached a couple of times in the last few years by first a company and then a law firm representing a company that is not located in Illinois, but that does business in Illinois for other companies, that was being sued, and the size of the damages that were being asked in the lawsuit against them would literally put them out of business. I read the Biometric Information Privacy Act and had to tell them that there was not a way to say that they weren't violating the definition of what was a biometric, and so they had to go on to either find a different expert to work for them, or to find different ways of fighting against this law. So this law has been in the courts for several years now. It's going to be in the courts for several more years. And as each state introduces a similar law, and the fact that there could be 50 different, slightly different versions of this law among the 50 different states, it's easily going to be 10 years, the next 10 years hence, working out this sort of issue. What level of biometrics can be used with what level of explicit permission by corporate entities in a semi-public fashion. You've probably heard of EU General Data Privacy Regulation. That's sort of the big thing that covers all of the EU. And it's similar in spirit to the Biometric Information Privacy Act. And in fact, it's probably better to have a nationwide law on this form than 50 different state laws on this form. The EU is maybe a little bit ahead of us, or a lot ahead of us in that sense. A good colleague and friend of mine, Ross Beveridge, in corresponding with this, had some thoughtful insights, I thought, into what are the important issues here. And he said, what we need is some way to clarify the difference between public and private space and how face recognition technology is used in these two things. In the past, we've had this idea that face recognition used in a public space, because it was a public space, you had no expectation of privacy, and there was nothing wrong with using face recognition in a public space. Spaces, public spaces, online and physical public spaces. And at the moment, they are the only ones who have access to the data they collect. Should the public have access to data that private entities collect in public spaces, so that the power associated with having access to the data doesn't concentrate into a small number of hands who may or may not have the good of the population at heart. And data collection that is open enough so that citizens can know what is being collected on them and cause that information to necessarily be correct or stop being used and resold on them. So I thought Ross had distilled some important elements of the concept of how are we going to work out the use of face recognition technology in the next decade. The last subject I'm going to talk about, I've labeled it here, unsound research methods and goals. I'm going to give you some examples of things that are going on and things that are being used, some of which you should recognize, one of which at least you should recognize as just crazy. That's my subjective judgment of it. And some of which are maybe not crazy, but we have to think about them and whether or not they should be used, if they could be used. This is working into it because this is going to illustrate to some degree the problem of thinking that you have solved a research question that you haven't really solved. There's this research area of kinship recognition. That is, from two pictures, can I recognize whether or not the two people in the two pictures are related? Sibling and parent, or brother and sister, or something like that. This data set that was created out of the images that you see here, you notice that there's sort of family portrait images. And so the idea would be that you crop the face out here and crop the face out here, and you crop the face out of all these images, and you ask, well, can I figure out that this face is related to this face, but this face is not related to this face? When I say that, it's maybe not obvious, but all of the related pairs that we see on this slide, at least, whenever the two people are related, they're both in the same picture. So they're both cropped from the same picture. So if there's similarities between things in a picture and differences with things in another picture, that's confounded with whether or not the people are related. So when I decide that I can say that this person and this person are brothers, It may be only because they were in an image that was taken by a certain camera with a certain kind of lighting and a certain kinds of noise properties that allows us to pair those compared to any of the other images, face from any of the other images that we see. And that's essentially what was being said in this comment on this data field, that, yeah, you think that you're getting 70, 80% correct recognition of kinship, but when you use a data set where all of the face images had to come from different pictures, it drops to 50 or 60%. And if it's 52, it's really not that different from guessing related, unrelated, right? So it is possible to make an error of a certain kind in how you set up your experimental data, and for that to cause you to think you're able to do something that you're not yet able to do. So here's an example of something that at least some researchers think that they are able to do, that their neural network is able to do. Can the neural network be trained to determine the sexual orientation of the person whose face is in the image? This paper was actually published in a peer-reviewed journal, and they believe that they can do this. The images for people who are gay come from one source, and the images for people who are not gay come from another source. And so there's a very high correlation of different sources of images and the sexual orientation of the people in the images. This should present a question or a problem or a skepticism for observers of this work. Nonetheless, the researchers believe that they can do it, and people have been reproducing their work, extending their work, critiquing their work, and pointing out that in some societies, if it was believed that this algorithm was correct, this could present problems for the people labeled as gay by the algorithm. And so that's the immediate social impact of this work being believed and used in some countries. This is one of the examples that I think you should recognize can't really be possible. This group of researchers, and to my knowledge, this paper is not yet published in a peer-reviewed journal. This group of researchers believes they can determine from the face image of the person whether or not the person is a criminal. Again, they acquired a set of face images of criminals from one source, a set of face images of non-criminals, according to them, from a different source, and trained a neural network to be able to distinguish between the two, and believe then that they have an algorithm that will tell from the face image with 80-something% reliability whether or not the person is a criminal, and that they can then talk about the typical face attributes of criminals and non-criminals. My thought experiment for these authors, if I were to talk to them, would be along the lines of, let's assume that I've never committed a felony before in my life, but that today I had an irresistible insight into the perfect felony crime. You have a picture of my face from last week, a picture of my face from later today. It takes me a week to figure out exactly how to execute, because as I said, it's the perfect crime. It's going to take a little bit of preparation. It's a week before I actually physically commit the crime, even though my heart was in it from later today when I saw the possibility. Next week, I commit the crime. No crime is truly perfect. So 6 months later, I get arrested. 6 months after that, I get convicted. But 6 months after that, I get pardoned. What is this person's algorithm that predicts criminality supposed to say for each of those images? Will it change as I go, or does it need to produce the same thing for all of the images? And there you begin to see that this is not, for me, subjectively, this is crazy. You can't do what you're saying you can do, even in theory. So unsound research methods and goals, expect to see more people think that they can do things they can't do, and always look at the data. Be convinced that the data is coming equally from the same source for the two categories of things that they believe that they can separate. Now, normally I would take questions, but I can't because I'm pre-recording this for you. For the work done at Notre Dame, I have links here to papers that you can read about our work. A lot of the slides have the actual name and authors list, so you can go back and find any of those works. And if, as I said at the beginning, if you're a student in the class, you have my email on the first slide. Feel free to send me a note and ask questions at some point if you would like. Thank you very much, and I hope you enjoy this.